the world of modern technology, new concepts emerge from time to time, ideas that promise enormous leaps in how we live and connect. If the internet as we know it today reshaped the world over the past 3 decades, the quantum internet is expected to trigger an even deeper transformation in the decades ahead. Thanks to the efforts of the University of Pennsylvania team and other research groups worldwide, we can now imagine, more clearly than ever, how a quantum internet could rewrite the rules of communications and open new horizons in areas such as artificial intelligence, drug design, and the creation of advanced materials that classical computers alone could not realistically reach. At first glance, the term quantum internet may sound mysterious or far removed from reality, yet the core idea is straightforward. Leveraging the laws of quantum mechanics, the rules that govern the behavior of extremely small particles such as photons and electrons, to build a new communications network that is more secure, faster at handling certain kinds of information, and capable of linking quantum computers to one another around the world. Understanding quantum signals and the concept of quantum entanglement is crucial to grasping the potential of the quantum internet. Quantum signals rely fundamentally on entangled particles connected so deeply that their states become linked, even when they are separated across distance. If the state of one particle is changed, the state of the other changes immediately, in a coordinated way. This phenomenon is known as quantum entanglement. In the past, it was described as spooky action at a distance, but today it has become a practical tool actively exploited in research laboratories around the world. Through quantum entanglement, quantum computers could collaborate and share computational capabilities across long distances. Imagine a set of quantum computers distributed across different continents, yet operating together as if they were a single massive machine. This kind of cooperation could open the door to solving complex problems in record time, such as simulating molecules with high precision to design new drugs, or analyzing enormous data sets to train artificial intelligence models at speeds that were previously unattainable. But working with quantum particles is not simple. These particles are extremely sensitive to interference and measurement. The moment we try to measure a particle's state, meaning the moment we look at it, its quantum state collapses into a classical state we can interpret, but at that same moment it loses precious quantum properties such as entanglement and superposition. For that reason, transporting quantum particles through long networks without destroying their state is a major scientific and engineering challenge. This leads to one of the biggest problems in building a quantum internet. How can we benefit from quantum signals without directly measuring them and destroying their quantum nature? And how can we monitor the network, correct errors, and ensure that information reaches its intended destination if the act of measurement itself can endanger quantum information? How is a quantum internet different from the traditional internet? In the traditional internet, information travels as pulses of light or electrical signals that can be copied, stored, and resent repeatedly without a fundamental limitation. If part of the data is lost, you can request it again or rely on a backup copy elsewhere. In the quantum world, however, information, if it truly exists in a quantum state, cannot be copied in the way we normally understand, because copying requires measurement, and measurement destroys the quantum state. For this reason, the quantum internet is not necessarily intended to replace the internet we use for browsing websites and watching videos. Instead, it aims to create a new layer of communications designed for extremely sensitive tasks. Linking research centers that operate quantum computers, providing ultra-secure communication channels between governments and financial institutions, or supporting complex computations in high-stakes domains. In other words, we can think of the quantum internet as a parallel network that we may not interact with directly in everyday life as we do with the conventional internet. Yet its impact would be felt behind the scenes, through better medicines, more powerful technologies, and stronger security systems that protect our data. The role of the Q-chip in coordinating classical and quantum signals is pivotal. To overcome the obstacles associated with directly measuring quantum particles, the University of Pennsylvania team developed an innovative chip called the Q-chip. The chip's core concept is to coordinate classical signals, ordinary signals made of conventional light, with quantum signals, so that classical signals act as a guide that tells the network where quantum signals should go, without touching the quantum signal itself. This chip sends the classical signal first, allowing it to lead the way through optical fibers. Classical signals can be measured easily and can be adjusted and routed as needed, without fear of destroying a delicate quantum state. The quantum signal then follows behind it using the same path the classical signal has established, but without being directly measured. This approach can be compared to a train traveling along a long track. The locomotive represents the classical signal that leads the route and reveals the direction, while the sealed cars behind it represent the quantum signals carrying the precious cargo. We monitor the locomotive, ensure the route is safe, and know exactly where it is going, but we do not open the sealed cars or interfere with what is inside until they arrive safely at their destination. In this way, the Q-chip functions as a translator and coordinator between two worlds: the world of classical signals, which we can measure and control easily, and the world of sensitive quantum signals, which require special protection. Bridges like this are what make it practically possible to build a quantum internet on top of existing infrastructure, namely the fiber optic networks that carry today's internet. The real challenges of deploying quantum technology are numerous. One of the biggest challenges in transmitting quantum particles over commercial infrastructure is the constant variation in real-world environmental conditions. In laboratories, researchers can precisely control temperature, reduce vibrations, and isolate systems from noise and interference. But outside the lab, the situation becomes far more complex. Fiber optic lines stretching across cities and countries are affected by many factors. Temperature changes between night and day, seasonal shifts, vibrations from trains and cars, subtle tremors caused by construction, and even mild seismic activity that we may not notice but still leaves an effect at extremely fine scales. All of these factors can alter the phase or other characteristics of a quantum signal, introducing noise or breaking the quantum correlation between entangled particles. To address this, researchers developed a clever error correction method that exploits a key fact. The interference that affects the classical locomotive signal will also affect the quantum signal following behind it in a similar way. Since the classical signal can be freely measured, any unwanted distortion that occurs to it can serve as a map of what likely happened to the quantum signal. The system can therefore measure the classical signal and infer the correction that should be applied to the quantum signal, without measuring the quantum signal directly. This idea is like watching a person's shadow on a wall to understand how they move without touching the person themselves. In this way, the system preserves the integrity of the quantum state while still dealing with the environmental changes that are unavoidable in real-world networks. Even so, the road ahead remains long. Current technologies are still experimental and are often tested over limited distances and under specialized conditions. Expanding these systems to span entire continents will require massive investment, the development of more stable components, and broad international collaboration to unify standards and protocols. Potential applications of the quantum internet are vast and varied. Although the quantum internet is still in its early stages, the potential applications it promises are driving scientists, companies, and governments to race toward exploration. Among the most prominent applications are advancing artificial intelligence, designing new medicines, developing advanced materials, and ultra-secure communications. Quantum computers connected through a quantum internet could dramatically accelerate the training of large AI models, especially those involving complex data analysis or simulation of intricate physical and chemical systems. Instead of relying on a single supercomputer, computations could be distributed across a network of entangled quantum processors. One of the biggest challenges in drug design is simulating molecular behavior with high accuracy. Quantum computers are naturally suited to these kinds of calculations, and the quantum internet could connect such computers around the world, forming a vast virtual laboratory to test new compound molecules faster and potentially at lower long-term cost. A quantum internet could connect specialized research centers in physics and materials science, enabling collaboration on simulations of superconductors, new alloys, or materials with unique optical or mechanical properties. This could unlock innovations in renewable energy, electronics, and aerospace. Quantum communications, especially quantum key distribution (QKD), enable channels that are extremely difficult and perhaps practically impossible to eavesdrop on without detection. Any interference with the quantum state leaves traces that can be detected immediately, making the quantum internet a strong candidate for protecting sensitive data, whether governmental, financial, or military. Scaling the quantum internet is a formidable task. The next major step in developing the quantum internet is overcoming the primary barrier to scaling quantum networks beyond urban areas. One of the most important obstacles is that quantum signals cannot be amplified in the traditional way. In ordinary fiber networks, optical amplifiers boost signal strength as it weakens over distance. But quantum signals cannot be amplified easily without destroying the quantum correlations they depend on. Some research teams have demonstrated that quantum keys, special codes for ultra-secure communication, can travel long distances over conventional fiber using clever techniques that reduce the chances of losing quantum information. These systems typically rely on sending weak pulses of light to generate random numbers that cannot be copied, allowing two parties to create shared secret keys. This approach is highly effective for security applications, but it is not enough to connect full quantum processors operating at higher levels of complexity. Linking two quantum computers requires maintaining strong entanglement between qubits located in different places, and that demands a more sophisticated infrastructure than simply generating secret keys. For that reason, scientists are developing what are known as quantum repeaters, devices designed to extend the range of quantum networks without destroying entanglement. They can be thought of as intermediate stations that partially rebuild quantum links at each step, rather than directly amplifying a quantum signal. Combining technologies like the Q-chip with quantum repeaters could provide the foundation for continent-spanning quantum networks in the future. Will the quantum internet replace the regular internet? A natural question arises. Does the quantum internet mean it will replace the internet we use today? The most realistic answer is no, it will complement it. The conventional internet was designed for text, images, video, and everyday browsing, and it does so with high efficiency. The quantum internet is more like a special lane reserved for precise, sensitive operations that require quantum properties. It may take many years before ordinary users feel the quantum internet directly, but its impact will appear in the services they receive. In the quality of healthcare, the accuracy of weather prediction, the strength of data protection systems, and the emergence of technologies we cannot yet fully imagine. The study presented by the University of Pennsylvania represents an important early step in showing how a single chip can manage quantum signals over commercial fiber using familiar data routing techniques from the traditional internet. What appears today as an advanced experiment inside a research laboratory may in the coming years become a cornerstone of a new global communications infrastructure. Despite major challenges, ranging from the difficulty of preserving quantum states, to technical limitations in amplifying signals, to the high cost of infrastructure, current efforts are opening the door to a future filled with unexpected possibilities. Just as few people in the 1990s could imagine that the internet would become inseparable from nearly every detail of modern life, a day may come when we view the quantum internet as the invisible background that supports many of the technologies we rely on daily. The quantum internet is not merely a new technical upgrade. It represents a fundamentally different way of thinking about information itself, how we represent it, how we transmit it, and how we protect it. As research continues, as chips like the Q-chip are tested, and as quantum repeaters evolve, we may be witnessing the beginning of a new chapter in the information revolution, deeper and more complex than anything we have known so far.